overall, let's talk about some of these galaxy observations. We said in the last session that Hubble was using the Cepheid variable stars in different galaxies and using the period luminosity relationship developed by Henrietta Swan Leavitt. Hubble was able to start actually measuring the distances to different galaxies. We've also talked about how we can use the spectrum of these galaxies to measure how fast these galaxies are moving towards us or away from us. So again, Hubble had access to the best telescopes in the world at the time. So he was able to make these measurements of, well, how fast are all these galaxies moving? And as I've mentioned before, in science, when we start to gather data and get a large quantity of data, what we want to try to do is find patterns in that data. And Hubble was able to find a remarkable new pattern after making some of these measurements. Here is the pattern that we refer to as Hubble's law, and that's going to be the main topic for the rest of this session. So Hubble's law. He noticed that all distant galaxies are redshifted. So all distant galaxies redshifted. I.e. moving away. And the greater the distance to these galaxies, the more it's redshifted. So larger distance, more redshift. So all distant galaxies are moving away from us. And the greater the distance to these galaxies, the faster they're moving away. Again, Hubble was able to identify this because with access to the best telescopes, he was able to measure the distances to these galaxies. And by using the spectras, he was able to measure the redshifts of these galaxies. And this is a diagram of Hubble's data from 1929. Notice that we couldn't at that time see galaxies very far away from us. So this is showing a little bit of an upward trend, but it's pretty noisy because if you're really close, we said all distant galaxies are redshifted. In our own local group, there are even a couple of galaxies moving towards us. But as you get further away, those galaxies start to be moving away from us. But within just 2 years, the red shows the original data. Within 2 years, astronomers had been able to measure the distances to more and more distant galaxies. And now this pattern becomes much more clear, where the more distant the galaxies, the more redshifted they are. This is some more modern results. This is from a summary of some data from a whole bunch of surveys, including the Hubble Space Telescope in 2001. This is measuring the velocities of these galaxies and their distance in megaparsecs. So again, it's instead of using light years, they use megaparsecs for this one. And the different colors of these dots represent how were their distances measured. Notice the most common one for these very distant ones are these type 1a supernovas. Those are actually the white dwarf supernovas. Remember, we said that white dwarfs, these, when they accrete material and eventually explode, when they pass that particular mass limit, they are extremely bright and have pretty much the same luminosity. So they are fantastic to use as standard candles for measuring very, very large cosmic distances. We know their luminosity. Their luminosities are ridiculously high, so we can see them from very, very far away. So whenever we see one of these white dwarf supernovas go off in a distant galaxy, we want to measure the brightness of that supernova and use that to measure the distances to these galaxies. So again, this is our data, and basically this little part of the graph down here is how far off from that ideal line is this data. So it's all, or sorry, this is measuring approximately what is the something called the Hubble constant, which we're going to talk about in a minute. The slope of this line, there are actually newer estimates that calculate this slope to be a little bit smaller than what we have here, but we're just going to use this as kind of our baseline since this is the value that's quoted in the textbook. So the actual value is probably slightly smaller than this, but again, for the purposes of our course, we can use this number to a reasonable level of accuracy. As always, all of this data is subject to revision and increased precision. In any kind of measurements, there's always a certain amount of uncertainty in those measurements, so we are continually trying to improve how we make these different kinds of measurements. So there's actually an equation associated with Hubble's law. So let's talk about that one. So the equation that we're going to be using is velocity. So this is the velocity of the galaxy. So the redshift velocity of the galaxy equals the distance to that galaxy. So sorry, this redshift velocity, this is in kilometers per second. That has to be in kilometers per second for this equation to work. Is equal to the distance to the galaxy in millions of light years multiplied by what we call the Hubble constant. So this is the Hubble constant, which we're going to take that value to be 22 kilometers per second per million light years. It's got these kind of weird units associated with it. So what can we do with this Hubble's law equation? Well, the way that this is normally used is if I can measure the redshift velocity of a galaxy. If we have the spectrum, then we've already seen multiple examples in this session of how we can actually measure the velocity of that galaxy. So if I can get the spectrum, identify those spectral lines, measure that redshift velocity or that radial velocity, then I can figure out the distance. Basically, divide both sides by the Hubble constant, by this 22 kilometers per second per million light years. And that will give me the distance to that galaxy in millions of light years. Or, and this is much less often done because measuring those redshift velocities, if we can get the spectrum, we're going to be able to get that velocity. It's generally harder to get the distance. But we could, in principle, say, if I know the distance to this galaxy, I can figure out the recession velocity. How fast is it moving away from us? The vast majority of the time, we're going to be using this first step, though. If I know the velocity, I can use this pattern to figure out the distance to that galaxy. So let's look at an example. Suppose a galaxy is moving away from us at 18,000 kilometers per second. I want to know how far away is this galaxy. So we're going to use Hubble's law for this. Well, we know how fast the galaxy is moving. We said that velocity is 18,000 kilometers per second. So that's our value for v. We're trying to find the distance. And we know Hubble's constant, the 22 kilometers per second per million light years. So if I want to rearrange this and solve for the distance, all I have to do is basically divide by the Hubble constant. So divide by 22. So if I do 18,000 divided by 22, I get approximately 818. The units for that are going to be millions of light years. And that is my distance value. So again, not too tricky. Once we have that velocity, basically take the velocity, divide by Hubble's constant, and that will give you the distance in millions of light years. Those are the units associated with that distance. Let's look at another case. Suppose you're given this spectrum of a galaxy, and you want to identify how far away this galaxy is. Well, we're first going to have to find out how fast this galaxy is moving. So we're going to have to use the same method of the Doppler shift equation. So we're going to have to go back up here and use that Doppler shift equation. If we look at the hydrogen alpha line, that rest wavelength is 6563. I should mention, if I haven't done this before, if I haven't mentioned this before, I do not expect students to memorize these rest wavelengths. They will be provided to you on homeworks or on the exam. I don't expect anyone to memorize these. But this hydrogen alpha line is showing up at 6563 angstroms. On this spectrum, it looks like it's showing up around 6900 angstroms. In fact, I think this was the one that we did before. So pause the video, redo that calculation if you don't remember what we got for that one. And then once you have that velocity, try to finish off the Hubble's law part of this and calculate what is the distance to that galaxy. So pause the video and try to go through these calculations. Okay, so in this case, we can measure, well, how much has that wavelength shifted? We get that redshift, and we can figure out, yeah, we said this was around 15,300 kilometers per second for the speed that this galaxy is moving at. So if I want to find out how far away this galaxy is, now we use Hubble's law. So our velocity is 15,300 kilometers per second. And that's the distance times the Hubble constant of 22 kilometers per second per million light years. And we're dividing both sides by that 22 value. So for the distance, when I do 15,300 divided by 22, I get around 695. And the units for this are in millions of light years. So again, we're able to use this to measure very, very large cosmic distances. So if we want to know the distance of this galaxy, we've got Hubble's law. We're going to rearrange that, and we get around 695 million light years away for this galaxy. So from Hubble's law, let's kind of review real quickly. We said for Hubble's law, all distant galaxies are redshifted. They all seem to be moving away from us. And the larger the distance, the greater the redshift. And we have this particular mathematical pattern to describe those galaxies moving away from us. You might want to say, well, what does this imply? Why are all these galaxies seem to be moving away from us and moving away from us in this particular pattern? Well, this implies that our universe, space itself, is expanding. There's a couple of different models that we can use for this to describe, well, how do we think of this expansion of space? We're going to talk about some of these models. Some of them are better than others. They all have some of their limitations because this is just something that's pretty difficult to visualize, since it involves a couple of things in general relativity, but let's talk about some of those background ideas. So let's talk about general relativity very, very briefly. So Einstein's picture of gravity. Let's talk about this. The basic idea of general relativity is what we perceive as this gravitational force is basically the effect of how the geometry of space and time, how we actually measure distances and how we actually measure times, that is actually affected by massive objects or by large amounts of energy. The basic idea is this: the geometry of space and time are changed by the presence of matter. So matter and energy change the geometry of space and time. That curvature of space and time tell matter how to move. So the curvature of space-time tells objects how to move. There are a whole bunch of different analogies that are made for this. The most common one is probably the rubber sheet analogy. Imagine a large rubber sheet, and I place a heavy mass on the middle of that rubber sheet. Well, that mass is going to push down the sheet, bending the shape of the sheet around it. And if you were to say roll a marble along that rubber sheet, well, that's going to be deflected because of how that rubber sheet has been curved. But and again, I don't want to go into too many details here. This is a kind of favorite topic of mine, but for the purposes of this course, I want to keep this as brief as possible. The point that I want to make right now is that there are other ways for the geometry of space and time to be warped in different ways. And as a separate part of this, the geometry of space and time can and will change over time. So this geometry of space-time can change over time. And this is what we talk about when we talk about the universe is expanding. It can change in other ways too, but right now our universe seems to be expanding on very, very large scales. So let me actually kind of clarify: expanding on very large scales. On very large scales. So again, on large scales, the universe is expanding. But there's a couple of very important points about this expansion that I want to make. Let's say I've got a universe. Let me zoom in on this a little bit so we can see this a bit better. Let's say I've got a universe consisting of Einstein's head. And let's say I live on Einstein's nose. And I'm looking at different points in the universe. I'm looking at part of his eyelash and a tuft of hair up here. If the universe is expanding, if this Einstein face is expanding, the point that was close to me, the point on the eyelash, has expanded away, but not very quickly. The universe has expanded. That point on Einstein's eyelash has moved away from me, but not super quickly. Whereas that tuft of hair, that's moved much further away. The further away the objects are, the faster that seems to be moving away from me due to the expansion of the universe. Also, notice that in all directions, when I'm here living on Einstein's nose, everything seems to be expanding away from me. Einstein's chin is moving away from me downwards. Einstein's cheek is moving away from me, kind of to the right. Everything seems to be moving away from me. But let's say, so I might want to say everything's moving away from me. I'm at a very special spot in this universe. But let's take another observer living in Einstein's ear. Well, maybe there's a wrinkle that moves away from them. Well, they will see that wrinkle moving away. Wasn't very far, so it's not moving away very quickly. This other tuft of hair, well, that part is further away and it's moving away much faster. And notice the observer on the ear is going to see everything moving away from them. And the observer on their ear is going to say, oh, look at me. I seem to be in a special location in the universe. Everything is expanding away from me. The point that I want to make with this is that for this kind of expansion, all observers at all different points in the universe see this universe expanding away from them. And the further away the object is, the faster the expansion. So for this model, at every point in the universe, they see this expansion where everything is expanding away from them, and the further away that object is, the faster it's expanding away from you. At every point in the universe, everything is expanding away from you. And further away, it's moving faster. And again, this is true for all points in the universe. There is no point in the universe where we can say, oh, this is the center of the expansion. There is no, as far as we can tell, there is no such thing as the center of the universe. It's not, when we talk about the Big Bang in just a couple of sessions, it's not that the Big Bang happened at one empty point in space, and there was at one point in space, and there was a whole bunch of empty stuff around it, and it expanded away from that one point. All of space is going through this expansion. So there is no center to this expansion. No center or even other special points. No center or special points to the expansion. I kind of like to use, when talking about this, the expansion of the universe, I kind of like to use the balloon model. No model is perfect. And I'm going to try to point out some of the weaknesses in this, but here's the basic idea. Imagine a balloon. And our universe is specifically the surface of this balloon. So our universe might have a couple of galaxies, kind of spread out in different locations. As the universe expands, that's like the balloon getting puffed up. If I can draw this. This is the limit of my artistic abilities, but again, as this balloon is inflated, those galaxies on the surface of this balloon are going to spread out. And the further away the object is, if it's a nearby object, it's not going to be moving away very quickly. If the object's further away, it's going to seem like it's expanding away faster because of the nature of this kind of expansion. But there's a couple of limitations to this model. First, we're talking specifically about space on large scales, like the distances between clusters of galaxies. A couple other things. So this expansion is only on large scales. Expansion on very large scales. So kind of like distances between galaxy clusters. In this balloon analogy, there is no inside or outside of the balloon. The universe is just the surface of this balloon in this analogy. So again, if we're looking just on the surface of this balloon, there is no center to the expansion. There's no point on the balloon that we're saying is, oh, this is the center of the expansion. It's just the entire balloon inflating. All of those galaxies are moving away from each other. So there's no center, no edge to this expansion. It's not expanding into some empty space. Space itself is getting larger. So not expanding into anything. Space itself is just expanding. Again, this is not an intuitive kind of model to work with. We're talking about general relativity. We're talking about the large scale structure of space. These kind of models don't really come natural to anyone. So that's why I'm trying to go through and show the limitations of these models so we don't take these models too far. But again, this expansion is only on large scales. On small scales, like galaxy clusters and smaller, the gravitational attraction can be, or other forces can be great enough to stop this expansion on small scales. Our solar system, for example, isn't expanding due to the expansion of the universe because the gravitational attraction between the sun and all of the other planets is strong enough to keep that region of space kind of held together. When we look at our own Milky Way galaxy, compared to these scales is still considered small scale. The gravitational attraction of all those stars and gas clouds in our Milky Way galaxy, it's strong enough to hold our galaxy together. Same with our local group. It's only when we're looking on very, very large scales, like the distances between galaxy clusters, that we see this large scale expansion of space. So how does this cause that redshift effect? How does this expansion of space cause it to look like those galaxies, the light from those galaxies is redshifted and those galaxies are moving away from us? Well, let's revisit this idea of look back time. When we look at, say, the sun's pretty close to us, cosmically speaking. So it takes about 8 minutes for the light to reach us from the sun. We look at Alpha Centauri, well, that's further away, but still in our local neighborhood in the galaxy. So that light takes us about 4.3 years to reach us from Alpha Centauri. If I'm looking at a distant galaxy, the light would have had to have been emitted many millions to even billions of years ago. So when that light is emitted, that light originally gets emitted to us. And as the universe expands, and as that light is traveling, the expansion of the universe causes those wavelengths to get stretched out as well. We say we have this wavelength of light, but as it's traveling, space is expanding as well, and that causes these wavelengths of light to stretch. So as the universe expands, the light waves are stretched, and this is what we call cosmological redshift. So I'll put a quick comment about that. So cosmological redshift. It's not really that when we see the redshift of these different distant galaxies, it's not really that they're moving through space very quickly. It's this effect of, as the light was in transit, that light is the universe is expanding, and that light is being stretched out while it's in transit. So this cosmological redshift, the basic idea behind it is this. The further away the object is, the longer ago the light was emitted. So further object, light was emitted further in the past. Light emitted further in the past. The further in the past that light was emitted, well, the smaller the universe was at the time. So the longer ago that light was emitted, the more space has expanded since then. So if it's further in the past, the more the universe has expanded since that time of emission. Has expanded since then. And the wavelengths of light get expanded along with the universe. So let me kind of quickly revisit that with a couple of these, pictures to kind of help out. So again, the more distant an object is, the longer ago its light was emitted, that idea of look back time, and the more the universe has expanded since that time. Let's say this is the universe today. Well, if one of these nearby galaxies emitted its light earlier on, not too long ago, well, the universe hasn't expanded that much since then, so that light isn't going to be as redshifted. If I have a very, very distant galaxy, in order for that light to reach us today, that galaxy would have had to emit that light much, much further in the past. And since that time, the universe has expanded much more along with those wavelengths of light. So again, the further the object is away, the further in the past that light had to have been emitted, the more the universe has expanded since that time, the more redshift we're going to see. And again, this is the difference between cosmological redshift, the stretching of those wavelengths of light owing to the expansion of the universe, and what we generally call the Doppler shift effect, where the fact that an object is moving through space, if it's moving towards an object and giving off some waves, those waves are going to look like they're compressed. Or if it's moving away, those wavelengths are going to look like they're stretched. It's a different mechanism for getting that kind of redshift or blue shift. In fact, when we look at some of this data of velocity versus distance for different cases, we notice that these galaxies don't exactly follow the exact line that's predicted by Hubble's law. There are some that are moving away a little faster, some that are moving not quite as fast away, or some that are even moving towards us. And what we're seeing in these diagrams is that there are two effects that are causing this redshift. The actual physical motion of those galaxies through space, and the effect of cosmological redshift, the effect of the expansion of space itself. So if I have something like a galaxy cluster, where we have all these galaxies kind of orbiting around each other, we have two effects. Space itself is expanding, but those galaxies are kind of orbiting around each other. So maybe some of them are going to be moving away extra quick, or maybe some of them are going to be moving a little bit towards us, due to their own motion. So you've got this kind of swirling cluster of galaxies, but that whole thing is kind of moving away overall. So at larger distance, on these much, much larger scales, that's when the effect of the expansion of the universe itself is going to be the dominant effect. If we're at relatively small distances, or we have one of these clusters where lots of stuff is kind of swirling around more, if we're on these smaller scales, then just their own physical motions of these galaxies through space can overcome that local small scale expansion of the universe. So we can absolutely still have galaxies collide with each other. I can walk over to my piano. It's not like the expansion of the universe is stopping me from walking over to the piano, because this expansion is only on very, very large scales. A couple other things that we just want to note before we end out this session. If space is expanding, well, that means in the past, space must have been smaller. And it turns out if you keep on rewinding that clock, then eventually you get to a point where all of space was very, very compressed down, where space was, the geometry of space and time was all compressed. And this is going to be the first kind of point where it looks like we might be having this Big Bang model, this point of, at some point in the universe's history, all of space was in a really, really compressed. We had the entire universe in this hot, dense state, and space expanded from that into what we see today. Well, if the universe has only been around for a certain amount of time, then even if space is infinite in size, if something is far enough away, maybe light hasn't even had enough time to actually reach us. So for very, very distant objects, if the universe's age is finite, has a finite age, then there might be very distant objects where their light has not had time to reach us. So it's possible extremely distant objects are so far away, their light has not had time to reach us. Has not had time to reach us. And this is what we call the cosmological horizon. Where there could be stuff, there could be much, much more stuff outside of our visible universe. But it's so far away that in the approximately 13.7 or 13.8 billion years that the universe has been around, those objects are so far away that the light that they have emitted simply has not had time to reach us. Just like the horizon that we talk about on Earth, where the Earth is curving away, we can't see anywhere past the horizon because the curvature of the Earth is blocking our view. In this case, what's blocking our view of things that are further away is those objects are so far away that light simply has not had enough time to reach us from these very, very distant locations. Now, if we lived in a different part of the universe, our cosmological horizon would be a different region. Just like if you move to a different part on the Earth, your horizon changes along with you. It depends on where you're located. But again, just kind of pointing out this idea of the cosmological horizon. One last thing that I want to mention. This Hubble constant that we talked about right here, it has these weird units, kilometers per second per million light years. Well, kilometers and millions of light years are both distances. So if we give those the same units, we can actually get those units to cancel out. And we're left with 1 over seconds. Kind of a weird unit for this Hubble constant. But if we take the inverse of that Hubble constant, 1 over the Hubble constant, we can actually use that to get a time. If I do 1 over the Hubble constant, so 1 over 22, and the units flip as well, so instead of kilometers per second per million light years, I get seconds times millions of light years times over kilometers. Well, a million light years is 9.5 times 10 to the 18 kilometers. So I can cancel out the kilometers. And the units I'm left with is 4.3 times 10 to the 17 seconds, which is around 14 billion years. And this time scale is one of our first approximate methods of measuring what is the current age of the universe. Now, this kind of a method, this kind of saying we have this constant that we can kind of rearrange it into units of seconds. We wouldn't necessarily expect this to be more accurate than accurate within a factor of a few, maybe 2 to 5 times larger or smaller than the actual age of the universe. Because the actual age of the universe also depends on the composition of the universe, the different types of material, the energy density of the universe. So it is actually a bit of a coincidence that this rough approximation is as close to the currently accepted age of the universe as it seems to be. But in future sessions, we're going to be talking about this kind of concept of the Big Bang, identify the different phases in the Big Bang, what we know about the Big Bang, what we don't know about the Big Bang, our evidence for the Big Bang. We're going to be talking about this in a fair amount of detail over the next couple of sessions. So stay tuned for those ones.